Hello, I'm Sylvia Knight, Head of Education at the Royal Meteorological Society. In this series of short films, we're going to be covering some of the background information that teachers may find useful if they are teaching weather and climate at secondary level, and specifically if they're using our weather and climate teaching guide with accompanying classroom resources, which you can find on our website, MetLink. The water cycle moves water in its solid form, that's ice and snow, its liquid form, water and cloud droplets, and as a colourless gas, which is water vapour. In this film, I'll be focusing on the water cycle in the atmosphere. Most of the atmospheric processes ultimately depend on the balance between evaporation and condensation. And in some very cold places, direct transfer between ice to water vapour, that's sublimation, or vice versa, which is deposition. Critically, the rate of evaporation of water from a liquid to a gas depends on temperature. The warmer it is, the faster water evaporates. On the other hand, the rate of condensation depends on the concentration of water molecules in the air. Water is continuously evaporating and condensing from lakes, oceans, rivers, puddles, cloud droplets, vegetation, and much else. It's only the relative rates of the two processes that change. You often hear people talking about how much water vapour the air can hold, as if it was some kind of sponge. This misses the point that both evaporation and condensation are going on all the time. It also becomes a problem when the humidity is over 100%. And if you use that sort of terminology, that implies that there's more water vapour in the air that it can hold, which doesn't make sense. Another mistake to watch out for is people talking about the air condensing rather than just the water vapour in the air. Air is mostly nitrogen, which condenses at minus 196 degrees Celsius. So let's consider some air which is cooling. As it cools, the rate of evaporation will fall, but the rate of condensation will remain about the same. At some temperature, there'll be more condensation going on than evaporation, and at that point, cloud droplets will form. Making a cloud in a bottle is a nice way to demonstrate this process. You can find the instructions for how to do that on our website, MetLink. Cloud base is a nice visual reminder. Given that the temperature usually falls with height in the atmosphere, then the cloud base marks the height at which the temperature has fallen to the point where there is more condensation going on than evaporation. That's why the base of clouds is usually flat, unlike most primary school drawings of clouds. We can extend this thinking into looking at different types of rainfall. For cloud to form, the air must have cooled. One way that air can cool is by rising. Bearing in mind that air pressure is simply a measure of how much air there is above, then as the air rises, there's logically less above, and so the air pressure falls. As the pressure falls, the air expands. As it expands, it pushes against the surrounding air, and the air does work pushing the surrounding air out of the way. It loses energy doing that work, and so it cools. So as air rises, the pressure falls and the air cools, and at some level, it may reach the temperature at which cloud forms. There are several ways in which air can be forced to rise. Firstly, at weather fronts. If a front is simply the boundary between air which is recognisably different, usually in temperature, then a front marks the boundary between warmer and cooler air. The warm air will always rise over the colder air, and a teabag rocket is a nice way to demonstrate that. Cloud and rainfall may be the result. We usually get rainfall in the UK when the cold and warm fronts associated with low pressure systems pass over. Secondly, on a clear, hot, sunny day, some parts of the land surface may heat up more than others, maybe because of their aspect facing the sun or the surface colour if they're darker. The air in contact with the ground will be warmed in turn and subsequently start rising. Typically, this gives late afternoon summer thunderstorms with cumulonimbus clouds. This is classed as convectional rainfall. Then, if air of polar origin is travelling south, getting progressively warmed as it travels over increasingly warm land and sea as it goes further south, the air will eventually start rising, giving rise to puffy cumulus clouds. Again, this is convectional rainfall. This satellite image from the North Atlantic in winter clearly shows the puffy cumulus clouds typical for polar maritime air. Air can also be forced to rise because of a change in the height of the Earth's surface, either a coast or hills or mountains. If air is forced to rise because of the underlying topography or orography, which is relief associated with hills and mountains, then it may again reach the temperature at which cloud droplets form. Frequently, orography just enhances the rising that's already occurring. For example, in this satellite image, which we've looked at previously, you can clearly see that the isolated patches of convection over the ocean come together into a blanket of cloud off the west coast of Ireland, Wales, Scotland and England as the westerly winds hit the west coast of the British Isles. This image shows one day's accumulated rainfall over the UK on a day when polar maritime air dominated. So the wind's coming from the west and it's places in the west of the UK which are getting the most rain. The wettest inhabited place in England is in Seathwaite, where rising polar maritime air is pushed further upwards by the Cumbrian Mountains. Annual rainfall at Seathwaite is over 3,500 millimetres. Cribgoch in Wales receives over 4,600 millimetres, and several places in India receive over 10,000 millimetres of rain each year through this process. There'll be less rainfall downwind of the hills or mountains in an area known as rain shadow. The driest place in the UK, St Osyth, is in the rain shadow of our prevailing westerly winds. So if the air rising up the side of a mountain and cooling as it rises reaches the top of the mountain and is still warmer than the surrounding air, then it will carry on rising, leading to towering clouds over mountain ranges. Sometimes the air which has been forced to rise over a mountain and then starts sinking again when it's past the mountain overshoots on the way down, leading to a downstream wave with lenticular or lens-shaped clouds forming wherever the air is rising in the wave. When the cloud droplets in the cloud have grown big enough to fall as rain on the upwind side and top of the mountain, then there's obviously going to be less liquid water left to evaporate again on the downwind side of the mountain as the air is sinking and warming. So less heat is taken out of the air by evaporation on the downwind side than was released by condensation on the upwind side. So the sinking air ends up warmer. That's the Föhn effect. Air can also rise when air comes together near the surface of the earth, squeezing the air together and pushing it up, for example, because of sea breezes. Lastly, air also rises when air high in the atmosphere diverges and air rises up from below to take its place. This can happen where the jet stream is slowing down. However, cloud, and therefore rain, can form when the air is cooled by other mechanisms as well. So firstly, air travelling north from the tropics, particularly over the oceans, is cooled from below as it travels north. It can be cooled to the temperature at which cloud forms again. As this air is not rising, the cloud formed is of level sheets, stratus clouds, rather than the puffy convective cumulus. The cloud droplets rarely get big enough to fall as anything heavier than drizzle. Here is a typical satellite image for tropical maritime air, clearly showing the swathes of featureless stratus over the North Atlantic. The air can also be cooled from below in late autumn, winter and early spring, when there are clear skies overnight. The Earth's surface loses heat to space, cooling and in turn cooling the air directly in contact with it. This can lead to fog or low cloud forming. This sort of cloud, again, rarely produces anything more than a very light drizzle. Simple weather apps, typically those embedded in cheap weather stations, watches and things like that, use pressure as an indication of when it will rain. When the pressure falls, the rain symbol appears. But considering all of the different mechanisms for rain formation that we've talked about, only frontal rain is associated with low air pressure, as well as possibly the convection when associated with summer thunderstorms. So for many places in the UK, the prevailing wind direction is much more important. If air has travelled over the Atlantic to reach us, so if it's polar or tropical maritime air, then rain is likely on the west coast. Similarly, the east coast can expect rain or snow when the wind is blowing from Siberia, picking up moisture as it crosses the North Sea, so polar continental air. As water vapour condenses into liquid water, latent heat is released into the atmosphere. When air is warmed and begins to rise, the effect is enhanced by the release of this latent heat, which warms the air further, enhancing the rising motion. The heat release is the energy source which powers developing storms, whether they're mid-latitude depressions or tropical cyclones. It's only while cloud droplets are forming that there's an energy source. Conversely, when liquid water evaporates, it takes heat from its surroundings. We've all experienced of this as skin feels cold when it's wet. It's also worth noting that cloud cannot form in clean air. The cloud droplets need cloud condensation nuclei to form on. Typically, these might be soot from natural fires, pollen, salt, or even bacteria in the atmosphere. This can lead to it being cloudier when it's more polluted and forms the basis for cloud seeding experiments and even some proposed forms of climate engineering for mitigating climate change. If there aren't enough cloud condensation nuclei present in the atmosphere, the relative humidity can be over 100%. In the UK, we can get flooding in the winter when rain falls on ground which is already saturated from previous rain, or in the summer if an isolated thunderstorm causes rain to fall on ground which has been baked hard and dry by the sun. In both cases, the water runs off quickly into the streams and rivers and causes flooding. Whereas it's the Met Office that issues alerts about extreme weather, it's the Environment Agency that warns people when there is a flood risk. About 10% of the water evaporated from the ocean is transported over land by the winds and finds its way back to the ocean following condensation into clouds. Eventual precipitation is rain or snow and subsequent surface runoff and subsurface flows. As the climate warms, the whole water cycle intensifies. This is driven by an increase in evapotranspiration at the ground, but is controlled by the temperature of the troposphere, so the lowest bit of the atmosphere, which determines how much condensation and therefore precipitation occurs. Over the last century, northern mid-latitude precipitation has increased, and the number of heavy precipitation events over land has increased in more regions than it has decreased, particularly in Europe and North America. Globally, water vapour concentration in the lower atmosphere has increased by 3 to 4% since the 1970s. Water vapour is itself a greenhouse gas. So water vapour is a strong and fast feedback that amplifies changes in surface temperature that are responding to other changes, for example, increasing carbon dioxide in the air, and it multiplies that by a factor of 2. Many human and natural systems are highly sensitive to changes in precipitation in river flow and soil and groundwater. In the next film, we're going to look at polar climates.